So now we will continue with a C-film deposition. So today we will talk about a spatter deposition. So here is the basic setup for the spatter deposition. So we have the electrode, or this is the target. This is the target, like a gold, aluminum, but this is the target. And we put the wafer here. This is the wafer. Then we put the wafer on the anode. And we have this argon plasma with argon plasma. So we need plasma to make argon ions. So we have a lot of argon ions. The argon ion bombards the target, and the metal atom will be bombarded away from on the wafer. This is how the deposition takes place. So the pressure is about 1 to 100 milliliter. It's better for depositing alloy and compound than evaporation. So we know that for evaporation, we cannot deposit alloys with the same composition. So the plasma contains equal number of positive argon ions and electrons, as well as the neutrons. But actually, there are in a typical spatter deposition machine only a very small percentage of atoms are ionized. But mostly it is still argon gas, not iron. So the spatter can be run in both DC and RF mode. RF means a radio frequency, 13.56 megahertz. So the radio frequency is typically 13.56 megahertz. So the process parameters include the pressure, as I said, 1 to 100 milliliter, power a few hundred watt. For the DC spattering, the voltage is a few kilovolt. We can do additional substrate barriers, and substrate temperature is typically from room temperature to high temperature. So this is the photo for the target for the spatter deposition. So in addition to the IC industry, as we talk about for this course, a wide range of the industry products use spatter deposition. For example, liquid crystal display, so the electrode. So electrode material for the liquid crystal display, computer hard drive, magnetic layers. The hard drive is magnetic recording, so the magnetic layers is deposited by the spatter deposition. Hard coating for tools and metal and the plastics. It's more widely used than evaporation. So because for evaporation, we have very few things can be tailored to tune. We have very few things can be tailored to tune the film property. And the step coverage for evaporation is not good, and it is not suitable for the compound and alloy deposition. And we have lots of material waste deposited on the chamber wall and wasted. For the spatter deposition, so the advantage, so we can do in situ cleaning prior to the film deposition. So what we do, so we have argon ion. We have wafer here, so we can reverse the potential so that the argon will bombard the wafer to clean the wafer. So the film quality and the step coverage is better than evaporation. So this is because the items like aluminum atom or gold items, those items, they are more energetic, and the film is also dissipated by the ion bombardment. This makes the film a better quality. And deposition is more reproducible than evaporation. We know that for the evaporation, a small change of the temperature can leave a big change of the deposition rate. As a result, for evaporation, we need a quartz crystal balance to monitor the film thickness. But for the spatter deposition, we do not need to monitor the film thickness because the film thickness is very predictable if you know the power, the pressure, and the recipe. So we can use large target to get uniform film, and the target material can be used for many depositions. So you can see the target is very big. So this can be 80-inch target. So you can deposit many wafers by using the same target. But for the evaporation, you need to change the source material frequently. And there are no auxiliary damage. The disadvantage, so we have substrate damage by the ion bombardment. And we have higher pressure that can have some contamination if the gas is not very pure. The deposition rate is very slow. This is a big problem. So typically we get 10 nanometer per minute. For evaporation, we can get a 10 times higher deposition rate than spatter deposition. Some material like organics will degrade because of ion bombardment. And most of the energy incident on the target becomes heat. This must be removed. So we can do the alloy spattering. So we know that for evaporation, the composition of the alloy is different from the composition of the source material. But for the spatial deposition, the composition of the alloy is the same, approximately the same as the target material. So this is because for spatial, the target is not melted. But for the evaporation, like gold, we talk about gold, the gold nickel alloy. So for evaporation, the material is melted. So when they are melted, the gold from below can come to the surface, gets deposited. But for the spatial deposition, at the very, very beginning, maybe you have more gold coming out than nickel. But at the equilibrium, the gold and the nickel, they come out at the same rate because the target is not melted. So now let's look at a plasma. So plasma is ionized gas. With nearly equal number of ions, electrons, and neutrons. These neutrons include the gas molecules and the free radicals like atomic oxygen, hydrogen, or fluorine. So glow is because of the de-excitation of the excited argon. So glow means light. So we have the light. So we can use the glow as the display. So we know that maybe not now. So a few years ago, you can buy a plasma TV. You can buy plasma TV from the supermarket a few years ago. But nowadays, the LED TV and more popular. So we can use the glow. Of the plasma to make the plasma TV. So here we have the cathode glow. So glow is because of the electron excite argons. We have the cathode glow. So in this case, so we have the argon ion. This argon ion collide with the target, collide with the cathode to emit electrons. So these electrons will excite. Argon. Then we have the glow. But at this place, so we have this called cathode dark space or sheath. So here, electron move too fast, move very, very fast. There is not much collision with the argon. There is not much argon ion. So that's why this area here is dark. So this is the main plasma. So we have the glow here. Main plasma is bright. Here we also have this is also dark. So this is what is called the anode sheath. So this one here is called a cathode sheath. This one here is called anode sheath. So we have the sheath here because the electrons here they get lost to the anode. So there is no electron here, then there is no excitation of argon, then there is no glow. So this is also dark. So now let's continue to look at the property of the DC plasma. So thermal energy is given by something like this. So the V is given by kT over m is about 400 meters per second for the argon. For the electrons, is about 10,000 meters per second. So when the argon ion with energy 100 electron volt, this gives 20,000 meters per second. For electrons with 100 electron volt, the speed becomes 6 million meters per second. So we know that for the thermal energy, it's only 10,000 meters per second. So this is very, very fast. We have very, very fast electrons. Because electrons move so fast, so the plasma is highly conducting. It's very, very conducting. There is no little voltage drop. You can see here. This is the plasma. But here, so here flat. There's no voltage drop. No voltage drop in the main plasma because it is very, very conductive. So there is voltage drop only when when electron gets lost. So here in this case, electron here get lost to the cathode. Electron here get lost to the anode. So there is not much electron here and not much electron here. So we have the voltage drop here and we have the voltage drop here. So this electron gets lost. This is because of the thermal movement. The thermal movement, electrons randomly hit the target and get lost. So therefore, the plasma is always positively biased relative to other electrodes because electron gets lost more to the electrode than argon ion. So we have more electron lost than ion lost. So the plasma we have some positive charge in the plasma bulk, positively charged in the plasma bulk. So it's always positively charged. This gives the barriers. This gives the barriers here. So this barriers here, because we have electron here, and we have positive ion, positive charge here. So we have this positive barriers. Now these positive barriers will accelerate the positive argon ion to strike the electrode. But the barriers near the cathode, near the anode, is very small. So here is about 10 volt, So there is no significant sputtering with the substrate. So the barriers on this cathode, the total barriers, this is the plasma barriers plus applied voltage. This is very high. So there will be argon sputter with the cathode for the sputter deposition. So here lambda D is the called Dirac length. This is the basic property of the plasma. So now let's look at how to ignite and sustain the plasma. So how the plasma is sustained. So we have the ions. So ions will make secondary electrons when they bombard the target, and the electrons will make ions when they collide with argon. So we have this circular, circling process. This can sustain the discharge. If we look at here, so the ions bombard the electrode to make electrons. So electrons bombard with the argon to make new electrons and also make new ions. Then this ion bombard the electrode again, and it will generate one electron. The electron bombard with argon gas molecule to ionize it. Then this ion come back. So this is how this back and forth. This is how the plasma is sustained. So we know that from the evaporation that for the gas, the P lambda equal constant is about 0.01. Lambda is the mean free path, and the P is the gas pressure. So we have talked about the mean free path last time. So we need many collisions to ignite and sustain the plasma. As a result, the D should be much larger than lambda. So we need many collisions. Too small distance, there will be too few collisions because electrons just get lost, goes to the wall or electrode without ionizing a molecule or atom. And there will also be too few ions to bombard the electrodes and generate secondary electrons. So the PD cannot be too small, because if so, the electron will get lost to the electrode. But if the PD is too large, that means the pressure is too high. There will be too many collisions. This will prevent electrons energy build up. The electron, before it can gain energy, is stopped by the collision. So there exists an optimal PD value to ignite and sustain the plasma. For the case of air, the optimal value is here, 0.5. PD equals 0.5 for the case of air. So this we need about, so this is 100 maybe. So we need a PD equals 0.5. We need about 400 volts to ignite, turn on the plasma. This is the breakdown voltage to turn on the plasma. So D is the plane parallel electrode. D is the electrode spacing for the plane parallel electrode. So now we look at the sputter yield, step coverage, and the film property. So here is the sputter process. So we have the incident argon ion. Some ion will be reflected, some will generate secondary electrons, and it can also sputter away the atoms. So this is what we want. So the argon bombard aluminum target to have the sputtered away aluminum atom and get deposited on the wafer. So in this case, the argon becomes neutral again. Another case is to generate secondary electrons. So argon hits the target to generate secondary electrons. So one possibility, it can hit the oxygen to ionize it. This oxygen can come to the film. This is bad. If the oxygen comes to the film, this is bad, because the oxygen will become aluminum oxide. Another possibility is that this electron come out to collide with argon molecule, to collide with argon gas molecule, to ionize it, and at the same time create a new electrons. That means so one electron coming in can create two electrons. So two electrons coming in can create four. Four electrons coming in can create eight. Eight electrons. So this is called impact ionization. So this each time we double the available electrons, then we have the impact ionization. This sustains the plasma. For the typical spatter, the ion energy is about hundreds of thousand electron volts, but energy of the spattered atom is only 3 to 10 electron volts. So energy for this atom is only 3 to 10 electron volts. And each argon ion can create about 5 aluminum atoms. About 5 aluminum atoms. So as a result, you can see, so the sputtering process is very inefficient from energy point of view. The 95% of energy gets lost to the target, and this causes lots of heating to the target. So this is a big problem. So high-rate sputter, because of the lot of heating, we need efficient cooling. Normally, we use cooling water running on the backside of the target. So the sputter species is normally a neutral. Usually, it is neutral. You can see here. This aluminum is neutral, not like this, not iron. It is neutral, mostly neutral. So energy of atoms of molecules sputtered at a given rate is 1 order higher than that of the evaporation. As a result, the film quality will be better. So normally higher temperature gives you better film quality. So more energetic, it also gives you better film quality. But because the sputtering yield is low and ion current is limited by the heating, so we cannot have very high current because we have too much heating. So the sputter deposition rate is very low. It normally is about 1 to 2 orders lower than the thermal evaporation. So now let's look at sputtering yield. The sputter yield is defined as the number of sputtered atoms per impinging ion. So we have 1 argon ion coming in, we may have 1 to 10 atoms sputtered out. So obviously, the higher the yield, the higher the deposition rate. If we consider a simple model, so we have 1 particle collide with another particle, how much energy this particle can gain. So we can have, by using the momentum and energy conservation, we can have this kind of formula. So here, similarly, the sputter yield is given by this formula. You can see, depending on the energy of the incident ions, the higher energy of the ion, the higher sputter yield. The masses of the ion and the mass of the ion and the mass of the target atom, and then the binding energy of atoms. The higher the binding energy, the lower the yield, and the incident angle. This is a term of the alpha. So the yield is not sensitive to the target temperature. So from this formula here, you can see, so gold and copper, chromium, for example, which one have higher yield? So gold will have higher yield because gold has smaller binding energy. So we know that gold is soft. If we do the scratch, if we scratch the gold will be scratched off. So it's very soft. But that means the binding energy is low. So we have a lower binding energy, you get higher sputter yield. So here is the sputtering yield as a function of ion energy. So first, higher energy gives you higher yield. And also, we can, as I said, gold has higher yield than chromium because the gold, the binding energy is low. If we increase the energy, for higher energies, the yield approaches saturation. The yield becomes saturated. If we get at very, very high energies, if you keep going, then the yield will drop, like here maybe say 50 kilo electron volt. At very high energy, the yield will drop, will decrease. So this is because if energy is very high, so we talk about this platinum, it's very high, this is the silicon wafer, it goes very deep. When it goes very deep, there will not much platinum atom get sputtered away. So the yield gets lower, we have very high energy. So this is something like implantation into the substrate. So the yield also depends on the incident angle. You can see we have some angle that's easier to sputter off the atom than normal than this perpendicular normal incidence. So usually you can see at 60 to 70 degree, we get the maximum sputter yield. Nearly 90 degree, if the argon ion gets like this, nearly 90 degree, the yield also drop because there will be no interaction. We have this too much glancing angle. So this is experimental result. You can see experimental result. You can see for most film, we roughly follow this curve. So we have this curve. So we get the maximum yield at maybe 50 to 60 degree. So the difference is for the gold. So gold has higher the yield at the normal incidence. So why gold is different? So because it is rough. If this is the silicon, this is the gold film. So if you have the argon ion here, it looks like we have the normal incidence. But if we look at here, if we look at the locally, we have the inclined. If we have inclined incidence on the local film orientation. So here the sputter yield dependent on the ion mass. So those are the ion atomic number. So we have those many ions. So here is the sputtering of silver, sputtering copper, sputtering of tantalum. So this is the target. And those are the ions. So what we can see here is that so sputter yield is maximum for ions with full village shells. That means the noble gas give higher the sputter yield. So this is the niobium, argon, this is krypton, this is xenon. So those noble gas give the highest sputter yield. So normally we use argon. So argon is cheaper than krypton and xenon. So it is cheaper and the yield is high, and also it is inert. This is also very important. Otherwise, if we use oxygen to sputter, if you can imagine, if we use oxygen gas to sputter aluminum atom, we will not get aluminum film. What we get, it will be aluminum oxide film. But if we use argon, we cannot have, we do not have something, aluminum argon, no such thing like this. So here is the sputter yield of element at 500 electron volt. So those are the noble gases and those are the elements. You can see here, if we talk about argon, so the noble metal like silver, this noble metal has very high sputter yield. So the carbon has the lowest sputter yield. So because carbon is like a diamond, it's very hard, very high bonding energy. So now let's look at step coverage for the sputter deposition. We know that for evaporation, we have something like this. This is a small source. For the small source, so we have narrow arrival angle distribution. So the arrival angle is mostly perpendicular to the surface. So when we have a large target, so we have this deposition. Then we have deposition from the left, deposition from the right, deposition from the top. And we have wider arrival angle distribution. So this is the isotropic flux arrival. This is anisotropic flux arrival. This one can have this kind of distribution. This is the case for the sputter deposition. So this is the standard sputtering. So we can tailor. The arrival angle can be tailored to some degree. This is the normal sputter deposition. So this one is called a long through. So target is far away from substrate, so we have more directional deposition. This is the collimated, so that we have more direct deposition because we have this collimator. However, this is also affected very much by the collision. So if the separation from here to here is much larger than the mean free path, then there will be many collisions. This collision will make it more. This collision will broaden the arrival angle of the species. But this lambda, for typically we have 10 milliliter. The mean free path is about 1 centimeter. Mean free path is 1 centimeter. But there will be many collisions before the deposition to the substrate. But this is the typical deposition profile. Typical deposition. You can see we have more film on the top, but the good thing is that we have some film on the bottom, and we also have some film on the side. As a result, the metal on the top and metal on the side and bottom, they're connected. This is good. This is good for the electrical conduction. Another factor that affect the profile is the add item migration. So normally the item for the spatial deposition is about 10 to 50 electron volt. This is 10 to 100 times that of the evaporation items. And we also have energy. We also have energy provided by the bombardment, by the ion bombardment. So if we have a silver atom come to the surface, then we have the argon bombardment. Then this way we also help it to move around. This bombardment will also help the silver atom to move around. So that means they have higher migration. It can move around. This move around make the film denser and also make the film a better coverage. For example, this is for the evaporation. It's very, very directional. This is for the spatial deposition. The atom come here, they can move around a little bit. This give you the deposition on the side wall, and also we have a arrival angle like this. So we have the deposition on the side wall as well. But for the evaporation, it's like this. So no deposition on the side wall. So this is the CVD. So CVD has the best step coverage. It's covered evenly, uniform deposition along the vertical surface and along the horizontal surface, same deposition rate. So we can tilt and rotate the substrate to give better step coverage. So what we can do more? We can do a substrate heating. So when we have substrate heating, it can move farther around. To give better step coverage. We can also apply the barriers to the sub-wafers. So when we have the barriers to the wafers, this one will be more energetic bombardment. So here we have the barriers to bombard the wafer. When we have this more bombardment, it also helps the item to move around, give better step coverage. But this will reduce the deposition rate because some of the silver will be bombarded away. And this will give you, because it will sparse deposited material off. This gives you smaller deposition rate. So now let's look at the zone model. So this model, I would say, is not so useful in reality, but this is popular model, so we will talk about this. The zone model is the film morphology as a function of the substrate temperature and the incident ion energy. So here is the substrate temperature over the melting point, over the melting temperature. And incident ion energy, this is electron volt. So for the spatter, we can have 10 electron volt. For the evaporation, it's only 0.1 electron volt. So for the spatial deposition, the lower, this is the pressure. So the lower the pressure, the higher the energy. So for the film deposition, so once with the wafer surface, the newly added items will migrate along the surface until they form a nuclei. Then the nuclei will capture more items to form island, and then the island will merge to form the smooth film. And this is roughly how the film is formed. So here we have the zone 1. So zone 1 is the low temperature, and also this is the energy, low temperature and the low energy. So usually zone 1 is the porous or amorphous film because of the poor surface mobility. So low temperature, low energy, there is no mobility. So this is not good. We have amorphous film. For example, if the metal is amorphous, then it will be easily oxidized. So this is not good. So zone 2 is this part, zone 2. So here we have higher energy. So we have the temperature is not very high, but energy is more higher energy. So when we get higher energy, we get this is most desirable. We get small green is polycrystal. This is the amorphous. This is polycrystal. It's dense and smooth film. So because of the higher surface mobility induced by this higher energy. So zone 3 here. So the temperature here is too high. So when we have too high temperature, we have large columnar grains. This gives you rough surface. So this is not very good. The zone 4 zone 4 at even higher temperature. We have even higher temperature, so we have more surface mobility, so we have very large non-columnar grains. So this will be a problem. The film will be very rough, and the light, when we do the lithography, the light will be scattered by the grains, and also the film is more rigid. The film is also more rigid. So this leads to the failure in the electrical lines. So this is not good. This is also not good. But this zone is good. So now we look at other issues: reactive sputtering, RF sputtering. So here first we look at reactive sputtering. For example, if we want to deposit titanium nitride film, so we can use titanium target. Another possibility is we use titanium target. Sorry, so here is titanium nitride. So we can use titanium nitride target to deposit titanium nitride film. We can also use titanium target and we add nitrogen into the argon. When we add nitrogen into the argon, then this nitrogen will come to the titanium atom to form the titanium nitride film. But this is the idea of the reactive sputtering. For example, we can use aluminum target by adding oxygen to form aluminum nitride. So here silicon oxide, titanium oxide, the same thing. Here is the titanium nitride. And for the carbide, we can add those gases into the argon, and then we use pure metal target to form the carbide. So this is called reactive sputtering. So reactive sputtering, it is popular, so we can do it here in the quantum nanofab clean room in the QNC building. The next important concept is the RF sputtering. RF means radio frequency. Radio frequency is 13.56 megahertz. So here, 13.56 megahertz. So this is good. RF is good for the insulating materials because the current cannot flow across the insulating target in the DC mode. So DC will not work with the insulating material, but RF will work with the insulating material. We know that for the capacitance here, we have the target here. For example, this is silicon oxide target. So then we have the kind of capacitor. So the impedance is given by 1 over I omega c. So this is the impedance. So higher frequency give you lower impedance. That means higher frequency can pass through this insulating material easily. So when the frequency is less than 50 kilohertz, both electrons and ions can follow the switching of the anode and the cathode. So that means when we have less than 50 kilohertz, so other ions, they will come to, at this moment, for example, this is positive, this is negative. Other ions will all the way get lost. Electrons will all the way get lost. So once the ion and electron get lost to the electrode, then once electron and ion are all lost to the electrode, the plasma will be turned off and the deposition will stop. But this is not good. So we need the frequency to be much bigger than 50 kilohertz. So in this case, we have 13.56 megahertz, but this is much higher than 50 kilohertz. So in this case, electron can still move like this. Electron can move far away. But the heavy ions can no longer follow the switching of this AC field, And the target also become conductive because this term will be small at this high frequency, so the target become effectively conductive. So because now the electrons gain energy from RF power, and we have oscillating electrons. So electrons move back and forth. But this is more efficient than the move one way or move this way. But when you move back and forth, it's more efficient to ionize. So it is more efficient to ionize the gas molecules. So as a result, RF sputtering is more efficient than the DC sputtering. So we can run RF sputtering at lower pressure because of the more efficient ionization. So then the question is, so here is the target, so here is the wafer. How do you know the argon ion will bombard the target, not bombard the wafer? So if the argon ion bombards the wafer, then there will be no deposition. So how to make sure that the argon ion will bombard the target only, not bombard the wafer? For the symmetrical target substrate configuration, so this is symmetrical. The same area. For the symmetrical case, it will bombard this one and bombard this one equally. For the symmetrical target substrate configuration, there will be sputtering of the both surface will occur, though they are in the opposite half cycle. So when the electrodes is not equal and not symmetrical, when the electrode area are not equal, so the field must be higher at the smaller electrodes, because they have higher current density to maintain overall current continuity. So the current is constant. So the smaller electrodes, the current density will be higher, because the smaller area, so J equals current divided by the area. So smaller area gives you bigger current density. We know that current density given by sigma is the conductivity times electrical field. So higher current density means higher field. The higher field means higher voltage. As a result, a smaller area gives you higher voltage. Smaller area gives you higher voltage drop, as you can see here. So when we have equal area electrode, we have same voltage drop here and voltage drop here, same voltage drop. But when we have unequal area electrode, so more voltage drop on the smaller electrode than the voltage drop on the bigger electrode. This V2 over V1 is given by V1 over V2 is A2 over A1. M is 1 or 2 experimentally determined. So the higher area, lower voltage. So as a result, so what do we do? So we make this electrode bigger. This electrode, we make it bigger. So we make the target electrode much smaller, and we make the wafer electrode much bigger. So the wafer electrode can even be connected to the chamber wall, which further increase the area. When we have bigger area, we have no bombardment on the wafer surface. So now let's look at magnetron sputtering. So why we need magnetron sputtering? So the purpose is to increase the deposition rate. So when we have magnetic field, then the electrons will be trapped. Electron will be trapped near the target surface, and it causes them to move in a circular way, in spiral motion. Every electron move in this way, in a spiral motion, is more efficient to collect and ionize the argon. So as a result, the ionization and the sputtering efficiency is much higher than the normal sputtering. The deposition rate will be increased by 1 or 2 orders. So when the electron moves in a circular way, it's more efficient to ionize the argon ions. So the wafer heating is also reduced because the plasma is confined near the target. You can see here. So here is the plasma here. So we have the plasma here, but no plasma, no glue in this target. So we have no heating to the wafer. And also we can use lower argon pressure. So because it is more efficient, because it is very high efficiency, so we can have lower argon pressure. We can still sustain ignite and sustain the plasma. So this is also good. The magnetron sputtering can be run in the DC and RF mode, but they are more often used in the DC mode. But RF mode is also very, very common. So here you can see, so here we have the electrical field. So the electrical field along this direction here, magnetic field is perpendicular. You can see here. So here is the target, and we put the magnet behind the target. So we have this magnetic field like this. Then the electron will move like this. Electron will move in a circular way. This way make it more efficient, make it more increase probability that they will collide with the neutral species and create ions. Now those magnets is very strong. I used to be responsible for sputtering machine. But each time it's very difficult to take the magnet off because they are too strong magnets. Now let's look at what is the radius. So what is the radius for the electron move near the target? So we know that m for the circular movement. So this is the force is given by mv squared over r. This is equal to. This is the Lorentz force. So we can cancel out one way. We can cancel out this way. So we have the r equal to mv over eb. So the radius given by mv equal to over eb. mv is the momentum equal to square root 2me. So e is given by. So we have this one. mv equal to the square root 2me. E energy given by 1 over 2 mv squared. But the energy is also equal to E times Vd. So E times Vd. So the Vd is the voltage drop across the dark space, across the sheet. It's a few hundred volts. So the energy of the electron is given by charge times the voltage drop. So if you put this one into here, into the mv, in the end, you get this formula here. For the case about 100 Gauss, so this is Gauss, 1g equal to 1 over 10 to the power 4 Tesla. So Tesla is the magnetic field. So 1 Gauss equal to 1 over 10 to the power 4 Tesla. For electrons, we can get 0.3 centimeter. So it really moves like this. But for the argon ion, it's 81 centimeter. So the argon ion, they are not affected too much by the magnetic field. As a result, we can see this is the non-magnetron substitution. We need a higher pressure. For the magnetron substitution, we can operate at a lower pressure, and we get lower pressure, and we get much higher deposition rate than normally non-magnetron substitution. And now we look at collimated substitution. So the goal is to fill high aspiration ratio holes by more directional substitution with narrow arrival angle distribution. So one way to do this is use the collimated substitution. So what do? We put a plate with high aspiration ratio holes. Then you can see most of the items like aluminum or gold. So most of the items will be trapped by this plate, and only those that go pretty parallel with the hole can come to the wafer. But this way we have narrow arrival angle distribution. But the problem is that this reduce the deposition rate considerably, because most of the items they got trapped by this plate. So another way to have narrow arrival angle distribution is to use it's called ionized substitution deposition. So in this case, the deposition items like aluminum is ionized. So what do we do? So we have RF coil. So we have the RF coil here. So when we have the coil, it will generate the plasma. But this plasma will ionize aluminum atom to form aluminum ions. But when it forms ions, so we have the barriers here. We know we have these barriers here. So we have the barrier voltage. So this barrier voltage, so when they are positively charged, it will go this way because of the barrier voltage. As a result, you can see we have more deposition on the bottom, and then the case of the broad arrival angle. The side wall, there is also some deposition on the side wall, but not too much. But overall, this should be okay to form the conducting film. So I will not talk about those two tables. You can take a look. Okay, thank you.